Hello Nidir. I thought I'll cover capacitance. This whole physics module of capacitance and like electricity and like charge related modules. I thought that we can just cover it through videos. I think it is going okay. Let me know if you want problem solving classes. Maybe we can do that. But I think conceptually this is good. If there are any conceptual doubts, we can again address them. But I hope I cover like these videos are meant to be topics where it's not as much about the formulas, but it is about the understanding of the subject per se. So a little bit of practice on that end is kind of left out in a way. So if I hope you're doing things on your end because otherwise you lag behind here. We can definitely keep a session just for problem solving because it is also important, but at the same time having an intuitive and understanding that kind of flows naturally to you is very important as well. So that's where I was going with this. So we'll start with capacitance and then we can start our way up from there. Okay. So capacitance in a way is really kind of a simple idea in a way. Uh, so capacitance or capacitors, the thing that have capacitance, as you will see, everything is indirectly a capacitor. Everything has capacitance, but what in an electric circuit you have a component which is kind of like a resistor. um, it's another component that looks kind of like that, these things, and so that's what we call a capacitor, right? It's an electric component. What does it do? So that's the question. So the first hint we have is in the symbol itself. So the symbol itself is a broken line parallel, right? And say if we connect it to a battery, right? So say if plus 5 volts here, and then we have connected it to a capacitor. It looks like the symbol is kind of telling us that the charge that's trying to flow, or maybe let's be particular exactly about that. So maybe the electrons that are trying to flow from the negative terminal of the battery into um, the plate of the capacitor kind of can't get into another plate. So there are two physical big plates, right? So as we talked about in the previous chapter, so these are essentially two different plates with uh, like two different metal plates with something in between them, but that something is not a conductor. So you can assume that it's just air between them, and some capacitors do have air in between them. Uh, it's just two plates, right? So the charges are flowing from one end, and then what do they do, right? Like they can't go ahead, go out from the other end. But the thing is, or can they? Right? So the way that works is all these electrons are coming in and they start depositing on the surface of this metal, right? So that creates like a negative field sort of a thing, and that tries to now the electron on this end now start to feel a little bit pushed away, right? Because these are negative charges, so they kind of start moving away from the wire. So what that creates at the end is like isolated positive charges here, right? Again, kind of like the sea of electrons that we always talk about. So there are these fixed positive ions, and the negative ions go away, negative electrons go away, and so what you're left is just the positive thing. So net positive comes in, right? Because the balancing charge has kind of gone. So we see that okay, one electron is coming in, then one electron is kind of going out from here, and but as a result, one positive charge is also created here, right? Yeah, so for the one negative charge that has just come in from this side, one positive is created, but as a result, current is still flowing. So you can kind of like, it is confusing in the way that if we had just a wire and one electron coming in and one electron going out, it is kind of like that, except the fact that you have one electron coming in and one electron going out, but that also builds up charge here on these plates. And slowly, you can imagine that the guy that's pushing the electrons from this side, right? Uh, so let's connect the negative end of the battery here because it's the electrons that we're talking about. So the guy that's trying to push has to push these electrons against the already building up negative charge here. So more electrons you push, the more negative charge keeps accumulating there, and then you find it harder to kind of throw electrons in, right? And at the end of the day, like what you have is this thing when it matches this power, right? Then kind of that transfer stops, right? So that pressure when it's equalized in a way, you can imagine that this is kind of like holding charge, right? This is storing charge, right? So that's the central idea. Uh, Stores charge. So capacitors, what they do is store charge. So that's kind of like you kind of throwing one electron here, and then it starts filling up, filling up, filling up, filling up to the point that you can't fill it up anymore because it is getting repelled, right? And so you have a whole bucket of negative charge. On the other plate, you have a whole bucket of positive charge. But what important point to note is if there is plus q charge here at the end, and then there is minus q charge here, right? So on the whole, it is still, if you consider the capacitor as a whole, it is still neutral, but you still have charge separation, right? That is where it has kind of storing charge. And of course, like that is kind of like the principle of a battery also. Like the battery is kind of like a big capacitor in a way, like that it had electrons to send. Why were these electrons coming from from here in the first place from the battery? Because the battery wanted to push those electrons to the other end of the terminal, right? Like how this negative and this positive wants to be together, like wants, but they are physically separated right now, so they can't jump. But at the end of the day, like they're still accumulating, and then there's a bunch of charges on both plates, right? So the way to think about this is the battery is kind of like, imagine that you have, like what we talk a lot about these hydro analogies. So an idea would be something like this. So you have two containers, say one with water, and or maybe yeah, like maybe we can bring this up at a later point. Maybe this is not the perfect analogy for this scenario. I'll just bring that up again. Anyway, so let's move on. So the idea behind the capacitor is that it is kind of storing charge. On a whole, it's neutral, but there's still charge separation. And the idea is it keeps accepting charge till its own pushing back power is equal to the battery's pushing power, right? So battery's pushing power is what we call the potential of the battery, so potential V. So this stores charge till the till this the capacitor's potential becomes V. Right, at that point, no current flows. Right, so just to be clear here, so at t equal to 0, this capacitor has zero charge, right? And we are talking about this circuit here, and this is say at V potential, right? So at t equal to 0, this has zero charge, and it starts flowing. So current is like, okay, like some current is there, maybe like 10 milliamps, right? At t equal to 1 seconds, you already have say like 10 coulombs of charge here, but your current you see is dropping, starting to drop now because it's not easy to uh, push charges anymore. So it kind of stops going in. The battery has don't does not have the power to push in, and at 20 coulombs maybe okay, it's like enough that it's starting to now stop, right? So and then you kind of see that at a larger time, now the amount of increase of charge is starting to drop off, and this is also starting to drop off. So you're kind of pushing charge, this is pushing new charge, right? So that is also kind of slowing down, and this process is also kind of slowing down. So like kind of at 5 seconds now you go up to 30, and this drops to 2 microamps, and maybe like that initial steep decline is kind of slowly coming, and maybe like after say 100 seconds you have almost like say 49.9 coulomb of charge, maybe if say 50 coulombs of the max capacity, and this drops to say zero point 0.1 microamps, right, which is very small. So what you see is a graph something that looks something like this. So it starts from 0, t equal to 0, and then this is the charge I'm plotting. So and the charge, sorry, so this is the current I'm plotting, and the current starts dropping with time, right? And similarly, the Q here, that starts increasing with time, right? And they're plotted on different say axes, so maybe it peaks up at some point, and say the max value it reaches after some time is 50, and this kind of starts from say 10 milliamps here, right? So like just to put labels on those axes, and then the way that it drops. So we see that both of these graphs kind of, especially this one, the blue one, looks like an exponential graph, right? And this exponential graph, if you remember, we had seen in nuclear decay, right? So we'll talk a little bit more about this towards the end, but this is what kind of what happens to a capacitor, charging of a capacitor, right? So you see that initially there is current flowing, battery can push charge, and then it's kind of stops pushing some charge, right, later. Okay, so that's fair enough. Now let's discuss what happens when you say now you have what you can call key charging of a capacitor. You have done charging of a capacitor is done. So that means now you have connected it to say a 5 volt battery. So this also has 5 volt, this also has 5 volts. The polarity is opposite to the battery. So because both the ones are on similar length, so we have to indicate where the plus is. In battery, it is okay. So this plus counters this plus. Hence, kind of like it kind of there is no current flowing, right? So once you charge the cap, we want to see now what happens. Now say this charge cap that we have here, right? Say we connect it to say a bulb. Now this was charged initially, right, at plus 5 volts, and because now we have connected, we have given a path for these uh, positive charges and negative charges here to kind of come together and neutralize. So there is a sudden rush of current, like so electrons go this way, so current goes this way, right? So there is a sudden rush of current that flows through from the positive plate to the negative plate, and they're like, okay, let's equalize, till the point that, of course, the voltage again, this is the voltage now across the capacitor. Now that also starts from 5 volts, and that also ultimately drops down to 0 volts, again falling like an exponential graph. So this is what we call discharging of a capacitor, right? So what happens is kind of like the bulb will have a sharp glow, and then it will just kind of fuse out. Imagine like a fuse blowing off, like something like that. Fuse does not work like this, but just an example about like your sudden glow, and then like the thing kind of neutralizes, right? So all of that energy that was initially pushed from battery to the capacitor, right, was stored on the capacitor. You will see that you say transfer X amount of energy, only X by 2 gets stored on this capacitor, and this X by 2 energy that was stored is then dissipated through that sudden burst into the bulb, right? So that's how the battery's energy slowly gets used up in steps. So the first step is only storing half of that energy that the battery is providing, and then using that half of the energy that you have. Right? Okay. So we'll get to these points a little bit slowly, but I'm just giving you a prelude of what is to come here. Okay. Uh, if we understand this, then let's start getting into how we tend to think about capacitors. So there is only one main formula per se, which where when we think about capacitance, that's how much charge are we storing, right? So we say that the charge that we're trying to store is proportional, will be proportional to the battery that is being kind of um, that has been put against it. So if you put a 2 volt battery, there'll be 2 volts equivalent amount of charge, something in coulomb, that will be stored. If you put 10 volts, then we saw that you can store twice the amount of charge, right? And in after a long amount of time, as we saw, like the charge kind of slowly builds up from zero to a particular fixed value on the higher side, right? Right. So and then we like similar to V proportional to IR, V proportional to I proportional to V. So we introduce the constant as R there. So similarly, the constant here is C, right? So C is say this characteristic capacitance of a thing. So this is the capacitance of a thing, of a capacitor, right? Like so, how much ability to store charge it is. Like so, if you kind of think about this like this, if you store if you have 1 volts, so how much charge are you able to store? So in one configuration, maybe you are able to store 2 coulombs. In another configuration, or with different materials, you are able to store 4 coulombs. So that inherently changes the capacitance of a thing, right? So capacitance looks like coulomb per volt. So this might be confusing a little bit. This is capacitance, and then this is coulomb, right, which is charge. So how much charge can I store if I supply 1 volt on that thing, on a capacitor? So that's the capacitance. So just to remember the units, so coulombs per volts, right? Okay, now we can start to kind of think about this a little bit more. So let's get into that. So the first thing that we want to discuss is how much energy are we storing. So so we said that energy is stored on a capacitor. Okay, so now the setup will look again similar to what we have done here. So there is a V battery here that is supplying some fixed amount of voltage, say maybe 5 volts, and say initially VC capacitance is 0 and the charge is also 0, right? Like, because we are just starting off, there is no charge buildup. But as we saw that the charge on the capacitor, right, is proportional to the voltage, um, is proportional to the voltage on the capacitor. So if you say supply, if you have higher voltage on across the capacitor terminals, then you will have higher charge on it, right? So you slowly start kind of building up from there. So you say that okay, this number will rise from 0 to 5 slowly as we saw. So this number will also grow, and this will grow in proportion to maybe let me. This will also grow to some number which will be C times 5 number, right? 5C. Let me write it like that, because it is Q equal to CV. C here is C and V here is 5. So it will go from 0 to 5C. But the question is, what is the amount of, so like the graph kind of will look like this. So if this is the charge that is we are kind of putting on the capacitor, and this is the terminal voltage across the capacitor. So mind you, this is always 5. But what is the capacitance's voltage? Say I put a voltmeter here, what will that read? So like the point is it will rise slowly, right? So it is starting from say 0, and when the charge is 0 until it goes to a certain point where this becomes 5C, at which point at the final voltage this becomes 5. So that slowly kind of matches, and this point, at this point, the current basically stops flowing, right? Okay, so the amount of energy that we say that is stored on this capacitor is this area, right? So energy is equal to half into Q into V. See, so in a way, so this is the energy stored on capacitor at the end, right? Now in the similar way, let's also look at how much energy did the battery spend, right? So if you remember, the work done by the battery was equal to Q times V, as we studied in a previous chapter or last year, I think. Q times V, right? So that's the amount of, so like just to remind you, power is equal to I times V, right? And power is equal to work by time, and I is Q by time into V, and this TT gets cancelled, so it gives us this formula right here, right? So in case you forgot, that's the little bit of derivation for you. Let me get rid of this. Okay. So that is this thing. So the battery is of course at this constant voltage V battery, right? And the charge that is supplied at the end is just again same as Q, right? Which is this 5C point here. So that becomes the work done by the battery. And you can see that this is what I was talking about. So if this is say X, so this is X by 2, right? So energy stored on the capacitor, which is the area under this graph, is half Q times V. But the battery's work, that's equal to Q times V again. But this V is a constant V, which is the final V. So it just becomes Q times V. And this becomes X, right? So that is X by 2. So the question is, where does this half the energy go? So we say that there must be some resistance in the wire. You will see that those wires kind of get heated up at the end. So that is where half of that energy kind of goes. So only in the process of kind of transferring energy from one place to the other, you have kind of lost the energy in the process charging up a capacitor. Okay, so but this formula is important, like this energy on the capacitor is equal to half qv, can also be written as, because q is equal to cv on a capacitor, so that becomes c times v square if you put q equal to cv here, or you can also write it as q is, again, v is q square by c here. So all three formulas are important, right? So similar to v equal to I square by r, and similar things, right? V square by r, I square r, and V into I, power, right? So these are similar formulas for energy of a capacitor. Okay, we are starting to kind of go into the depth. Okay, there are two things that we like to do similar to resistors here. So we like to put them in circuit, right? So one of the things we try to think about is, oh, like say I had one resistor here and one resistor here. So we said that this is say R1 resistor and this is R2 resistor. So this one becomes R1 plus R2. Or similarly, we have say R1 here and then R2 here. This became 1 1 by R is equal to 1 by R1 plus 1 by R2, right? So that was the parallel and series combination, right? In similar case, we want to do circuits for capacitors. So okay, so what is, how does that look like? So maybe this is C1 and this is C2. So here what happens is this reverses, and say you have two capacitors like this, C1 and C2, so then C becomes C1 plus C2. So you can always remember it as the opposite of resistance. So let's have a very short discussion on why this is the case. Why is it reversed, right? So in this case, if you think about it, if you have say a battery, right, and that's trying to push the charge in, right, so it's trying to push q amount of charge, that q amount of charge will kind of be split into top branch and bottom branch, so this q1 and q2, right? So q becomes split as q1 plus q2, right? But at the end of the day, we know that um, battery can only stop pushing when the pushing back power, like force match, right? And that force is kind of like everyone is responsible for their own force, right? Because say if this provides 5 units of force, five volts units inside, and this is kind of able to oppose with 5 volts, but then this say this is giving only 4 volts, so all of the charge will kind of flow inside, right? So everyone needs to kind of hold on their own weight and have enough pushing back power. So then that means the voltage here is also V battery, and voltage here is also V battery, and this is also V battery. Only in that case will be the final equilibrium condition where this pulling power and this pulling power is the same, right? So in that process, Q1 amount of charge must have gone up and Q2 must have gone below, and Q must have left the battery, right? So now we can similarly write like, so Q is equal to CV here. So this becomes C1 V. V is your V battery only, and then this becomes C2 into V battery. So V battery becomes common, right? And then say we have, say now we're trying to make an equivalent model which is C times say V battery. If there was just one capacitor in this case, so this was say C equivalent here. Same V battery is there. So what is this equivalent capacitance? That is what we are trying to find, right? So that just becomes equal to C into this. So same amount of charge must have flown from the battery to this thing, because battery should not feel like anything has changed if you replace those two capacitors. So that becomes C times V battery. So V battery cancels out, and similarly you have this formula that you get back, right? So very quickly, let's also discuss what happens in the other case. Maybe that will be a little bit easier to understand. But make sure you rewind the videos and kind of like see again like where what point you're missing. So this is say V battery here, and similarly a Q amount of charge now goes in. Now the thing is the Q amount of charge goes here, but Q amount of charge also leaves here, and the same Q amount of charge gives here, which comes back to the battery. So battery is happy, right? That it sent Q charge and got Q charge back. But the point is that charge kind of flew through two capacitors in this case, right? Now the pushing power of the battery, right, V battery, has to be opposed by Not just this, this is kind of like now they're kind of teaming up, right? They are kind of like pushing the battery up together, right? So the batteries, this thing must be countered by the first one and the second one together, right? And Q is equal to CV, so this is equal to Q by some C equivalent. So again, we replace always this thing by an equivalent circuit, as you can see maybe here. So both of these just are replaced with one equivalent capacitor. So that becomes similar to C by V equivalent, and then V1 becomes uh, Q, because the same amount Q has flown, Q by C1 plus Q by C2, right? And so you can cancel the Q's. So you get 1 by C equivalent is 1 by C1 plus 1 by C2, right? So like just to keep in mind about what things are happening, like you might not want to remember the derivation directly, but you have to understand the steps, because as you remember, the way that the current splits in resistors and the voltage across the resistors, if you remember, like say we had a complicated circuit like say like this, right? And then you have it connected to a battery, say this was R1, R2, R3. Then the way that you resolve this is you kind of go about first simplifying these two and then simplifying these two again, right? So there's one of that and then the new one. And so a similar approach you have to do here, and a question can be asked here: if I current kind of left the battery, then it must have split here into I1 and I2. Then what is the split, right? And we used to discuss that the split is kind of in I1 by I2 will be in the reverse ratio of R1 by R2, right? So similarly here, but if these are capacitors, uh, so if these are capacitors, then this would split as, because the relations are of the reverse, so that will split again in the same ratio, right? Uh, so this is something that we have to keep in mind. Uh, yeah, so this will be important. So how does it split is an important question that we have to ask. Okay, try to do questions from the book here. I'm trying to skip through those parts. Definitely go through these sections. Like I have explained the theory here, but go through these questions like 11, 12 here, and then maybe like I hope there are some solved examples, because you'll definitely get questions from this section, like stuff like this, right? So if these three capacitance are connected in series, what is the total capacitance? Like this is an easy, straightforward question. And then yeah, as you talked about, like these are opposites. Yeah, maybe this is an important topic. Like this is the capacitor networks topic that I'm talking about, right? So yeah, these are the things that we want to think about, right? Always try to kind of build up a mental picture that voltage on the capacitor is kind of how much it can push, right? So like if it wants to oppose say a battery, then it wants to have an equal pushing power as much as the battery has, right? So it will, the final voltage will be as much as the battery has, right? But say you have something like, because battery has say a constant pushing power, so in this case the this is 5 volts, and then at the end this will also be 5 volts, right? But say this is 5 volts now, the same capacitor here, this same capacitor, right, now is connected to a new undischarged capacitor, right? So imagine what would happen, right? So this is now fully charged capacitor at 5 volts, but it is kind of trying to discharge now because there is still a path, but at the end, like there'll be some charge distribution, redistribution in a way, right? Like so this positive charge will kind of now try to flow, but it will store on the other one. So as a result, as the final condition, you would have 2.5 volts here and 2.5 volts here. So something like, so it is kind of like the analogy they like to give in the book is, as I was talking about there. So it is, one is kind of like an empty tank, one is kind of like a full tank, because it is storing charge, it is storing water, right? So that charge, that water kind of flows through this pipe, right? And when that pipe kind of goes through, uh, both of these are kind of half full, right? So that's fine, that's fair enough. But one of the things that you don't understand is the potential energy in this case, right? The energy that was stored in the capacitor in this case is half CV square, half Q times half CV square, or half Q square by C, right? And say if the other capacitor was also same, and that becomes Q by 2 and Q by 2, right? So everything becomes Q by 2, so it becomes 4C, right? But that is now stored in two places, right? On both the capacitors. So this was, I hope you're understanding. So what we did is Q went from Q to Q by 2. So energy went to E by 4 because of this Q square factor, right? But then there are two times this energy because there are two capacitors, right, which are finally storing energy. So that final energy now becomes E by 2, right? Not E. So you started from E amount of energy, which is half Q square by C, but ultimately you're left with half of that ultimately, right? So the reason why, like, trying to think about this, like, so its potential energy is kind of here, like, and that kind of has come down, and both of them have kind of, like, it has dropped a lot, and then this has also kind of like risen a little bit, but the sum of total final potential energies of all that water is like lower than what it could have been from the initial. You might ask where the energy went, and again the energy kind of goes inside heating up these wires, so they become heated up. So these are things that, again, like, it's important, like, whenever you try to think about like these capacitance, should always think about them as like a water reservoir or maybe some kind of a storing thing, and then they have to provide some pushing force, which is kind of like water pressure from this point. And only, like, the only condition in which water does not flow is when there is equal pressure on both sides, right? So that pressure always has to be balanced, which is in electricity's case, that is voltage. So voltage must be balanced, right? Okay, I just try to go through these questions. Yeah, we have talked about these exponential decays. Like, the only thing that we have not discussed is the equation itself. So that kind of looks like this. So if you remember, uh, in activity, or so we said that n dropped from n e power minus epsilon these things, where this lambda was half life, right? Right. So this was n and this was t. Similarly, we had something called activity, which was dn by dt. That we also said is equal to some, like, a new constant, but like the similar same constant here, right? So this is called activity, right? Which is the change of how many, how many are decaying per in a specific amount of time, right? So this is the number of atoms that were undecayed, and then this was how many are decaying, like, in the process of decaying in that short amount of time, like whatever the short time is, maybe a minute or 5 minutes. So how many do you expect to decay? So that kind of was the concept of activity. And so similar to this, we said that this is an exponential curve, right? And similarly here we have, so in the case of discharging or charging of a capacitor, so in charging, the charge rises but the current falls, right? In case of discharging, the capacitor is already charged, right, with full capacitor. In that case, the charge itself falls, right? In the case of discharging. So just make note of my words here. So when you're discharging, say this is discharging circuit, and then this is a charging up circuit, right? In this case, both of these cases, the charge kind of goes through an exponential curve. In one case, kind of falls through an exponential. So in even in that case, you can say that, say say this is the circuit here. There is some resistance here, and this is some capacitance here. Then we say that the amount of charge that will start falling from the initial thing will be some initial thing minus e power minus t. Now, but instead of lambda, we have 1 by RC. So the lambda here is different. So this lambda is what we call time constant. So here kind of time constant is 1 by lambda in a way, and here time constant is RC, because they are kind of like, one is in the denominator and one is in the numerator, right? So we call whatever is in the denominator the time constant. Right? I don't know if you can see, uh, but yeah, maybe I can just show this here for the time being. Right. So this time constant is important. So this kind of gives you in a ratio about, like, how we used to talk about half life. We used to say that, yes, yeah. So we used to say that, yeah. So we used to say that in one half life, 66% of them decay, right? Something like that. So here in one time constant or tau, we say 66% of the charge has gone away, right? So it becomes 0.66 of that Q naught here. So this is after one time constant RC. Here after one half life, how many of them are left? There are 0.66 of them only are left. So there's a kind of like a similar thing that's going on. So it's very important for you to understand both the concepts here, including this activity concept, which is from a different chapter. Right, but your book talks about all of this, so make sure you kind of go through your book with the video that I'm kind of trying to show you here, and let me know if things are not clear. Okay, I'll see you. Bye bye.